For this video, I'm going to be going over Chapter 2.7, Derivatives and Rate of Change. So it's important to understand the applications of derivatives and where they come from, as well as what a derivative is. So first we're going to start off looking at this graph I drew. So this graph is just a function y equals f of x, doesn't matter. We have 2 points, p, which is a f of a, and then q, which is x f of x. And we have a secant line drawn right through those. So I think you could agree that the slope of this would be rise over run, or f of x minus f of a, x minus a. That's just a simple slope. For this graph I drew, we have something a little more complex. Same function, same secant line, but now instead of having two different variables, I have an h here. So 2 points, we have a and then a plus h. And then just f of a plus h, because once you plug this back in, you get that y value. Now the rise is f a plus h minus f of a, and the run is h. When you put that together, you see that this is just another slope equation. But in calculus, you want to be more specific, so we're going to use limits. Now, by using limits, we have just found the limit definition of a derivative. You may be wondering, why is this useful? Well, basically what we're doing here is estimating something nonlinear with something linear. And essentially, we're closing in on that x value to find that slope in that exact moment. So this h is used. We're finding the limit as h approaches 0 because we want h to become smaller. We want this to become closer and closer and closer to this a value horizontally and vertically. And as we do that, this secant line becomes a tangent line. That is why the derivative is the slope of the tangent line, and the slope of the tangent line can be used in applications of rates of change. Something many students find confusing is the difference between instantaneous rate of change and the average rate of change. The instantaneous rate of change is the value that the derivative gives you. So it can be used for the slope of the tangent line, the velocity or instantaneous velocity, the instantaneous rate of change of y with respect to x. That is the instantaneous rate of change. The average rate of change, however, is the average velocity, the average speed, the slope between 2 points. This is the algebraic approach. So both of these topics will give you a slope. However, it depends on how definite you want it to be. Instantaneous rate of change will give you at a certain point the slope, the change of y. The average rate of change will give you, in a given time interval, the slope, also the change of y. So this can be seen in this graphing example. We're giving this function, y equals 2x squared minus 2, in the domain 1 to 3 halves. This could be observed on the graph as well. The average rate of change is just y2 minus y1, x2 minus x1. When you solve it out, you get 5. The instantaneous rate of change, however, is using the derivative of this function, which can be used with x plus h minus f of x over h equation to find it's equal to 4x. You plug the 1 in, because that's the leftmost value, and then you get 4. Once again, you could see that 5 and 4 are not the same value. Another graphing example. This function is y equals negative 1 over x minus 3, 0 to 1 half is the domain. The average rate of change, once again, just the slope, y2 minus y1, x2 minus x1. See how it's using time intervals, so 0 to 1 half, and you get 2/15. However, in the instantaneous rate of change, we found the derivative to be 1 over x minus 3 squared, and we're using at the exact point we want at 0, the leftmost value, we want to find the change of the slope, or change of y value, which is the slope. That's 1/9. Once again, this is not the same value. Average and instantaneous velocity may be very similar and very close to each other, however, they are not the same, and that is very important to differentiate when you're solving rate of change problems. So now we're going to move on to the problems. The first problem is finding derivative of g of x, which is equal to x over x squared plus 1. We're going to use this equation, which we just went over, the definition of the derivative, which is gx plus h minus g of x over h. We're going to plug in x plus h in anywhere where we see an x, as observed here. And we're just going to subtract by the original function. To continue solving this, we want to get a common denominator, which is why we're multiplying by x plus h squared plus 1 times x squared plus 1. Once we simplify further down, there are terms we could get rid of. And once we do, we get negative hx squared minus h squared x plus h over hx squared plus h squared plus 1 x squared plus 1. By factoring out an h, we could further simplify and we'll eventually get negative x squared minus hx plus 1 x plus h squared plus 1 squared. After viewing this, we can see that the limit is h approaching 0. So anywhere we see an h, we're plugging in a 0. Once we do so, we find the derivative, which is 1 minus x squared over 1 plus x squared squared. The second example is a word problem of the instantaneous rate of change. It states the motion of a ball from a vertical height of 10 feet is given by st equals 10 plus 12t plus 3t squared. Find the instantaneous rate of change when t equals 2 seconds. Once again, we're going to use the x plus h minus fx over h formula. But since we have an x value, which in this case will be 2, we can directly plug in the 2. However, it doesn't matter if you plug it in now or later. Sometimes it's easier. So we're going to plug in 2 plus h into the original function, this one, and 2 into the original function. Once we simplify, we get 46 plus 24h plus 3h squared minus 46 over h. Factoring out an h, and as limit h approaches 0, so we're replacing h with 0, we get 24. This means that at 2 seconds, the instantaneous rate of change is 24 feet a second. Make sure to include units. That is another common mistake students make. Our last problem is finding the tangent line. Our function is y equals 1 over x minus 1 at x equals 3. We're going to need the y value and the slope, which we're going to use the definition of a derivative, which is written right here. Once again, if you know the x value, you could plug it in right away. Sometimes it's easier to do so. Sometimes it's easier to keep the x plus h, but you're going to put an x plus h wherever you see an x and subtract by the original. We're going to try finding the common denominator, and then when you simplify, we eventually get negative 1 over 2 times 2 plus h. The limit is as h approaches 0, so we could plug in 0 anywhere we see an h, and we get negative 1/4. This is the instantaneous rate of change when x is equal to 3. Now, the tangent line can be found with a point-slope equation. When x is equal to 3, y is equal to 1/2, so y minus y 1/2 is equal to the slope, negative 1/4, times x minus 3.